Welcome to the October 2024 meeting, and as usual I'll just quickly go through what has occurred in the last month, or some of the things in the last month. We'll start down in the bottom right hand corner where the University of South Australia and Flinders University have been working with NASA, and they've developed the equivalent of the maritime EPIRB system, the emergency positioning radio beacon, but the equivalent thing for use on the moon, because they are concerned that because there's not too many easily recognisable features on the moon, that when we get quite an astronaut presence up there, they could get disoriented and become lost. So they'd carry an EPIRB with them. And apparently that has a battery life of 10 hours, which probably exceeds the amount of oxygen that the astronaut is carrying with them anyway. So that was deemed to be a sufficient length of time. In the top right hand corner there you see the wavy line, and that's the light curve of T Corona Borealis. So if you remember, this nova was touted as having or being anticipated to go nova in and be visible to the naked eye sometime in the last month or so. But as you see the waviness there, in that chart, that's the last year of observations, and there's just under 80,000 observations worldwide being made of T Corona Borealis. And you do actually notice that the thickness of the line between the observations has actually broadened out in the last 6 months compared to what it was before. So things are starting to happen on the surface of it. Now these are all visual observations. There's nothing fancy here with fancy photometry involved. These are people measuring the brightness by eye and in comparison to the comparison stars. So I downloaded that data from the American Association of Variable Star Observers a couple of weeks ago, and as you see, no sign of an outburst yet. So that's about magnitude 10 there, so you're going to need binoculars or a small telescope to get down to there. You certainly won't see that by eye, but it should become quite bright when it goes into to nova outburst. Now the big thing over on the top left hand side was NASA launched the Europa Clipper mission off to Jupiter's second moon, Europa, and that was just the other day from the Kennedy Space Center down in Florida, Cape Canaveral. And that's on its way and will arrive in the Jovian system in about April 2030. So it's not going straight there, it's going to loop around Mars, use a bit of gravitational assist from that planet, fling it back to Earth, and then fling it round Earth, use gravitational assistance from Earth, and then throw it out at higher speed to Jupiter to get there in 2030. So a bit of a roundabout way of getting there, but that obviously has been the way to do it. Interestingly, with the launch window was 15 seconds wide. So they had to launch it within 15 seconds. Otherwise, they had to abort the mission. So, and why they allow that 15-second window is just in case a piece of space junk comes over at the wrong time. So it gives them a little bit of a leeway to get that junk out of the way, because there's so much in low Earth orbit that they don't want it accidentally running into it on the way. It would sort of make a very bad start to the mission if it got disabled fairly quickly. So it's well and truly on its way at the moment, and should be a very interesting one, trying to look for whether Europa and its sub-ice ocean has the right conditions for life on it. Now, one of the things they were concerned about with the Europa Clipper mission was the radiation level that it would receive as it came close to Jupiter. And there were several times in the last couple of months where it was looking like the mission might be delayed very substantially because they were worried about some of the instruments, whether they would survive the radiation level. It will come within about 25 kilometres of Europa, so really, really low down to the surface, and it will attempt to even go through the plumes of water being thrown into space off the surface of the planet and actually sample those as it flies overhead. So it's not going to land and take a sample, but it's going to fly through a cloud of mist being trailed behind the planet to actually sample what it's finding down there. Now, much like the Voyager missions, this one has a couple of plates attached to it. These are the two sides of a titanium plate. It's about 11 inches long by about 7 inches high, and that triangular shape. And on one side we have these wave forms here, which are audio wave patterns saying the word water in 103 different languages. So that's what all those little things are there. It also contains a microchip that's written on it 2.6 million names of everyone who wrote in to put their name on it. And so 2.6 million people's names will appear around the Jovian system in 2030. And on the other side is shown the Drake equation up there, which is the famous equation for the probability of intelligent life in the universe. And this poem on the back here by a US poet laureate, Ada Limns, called In Praise of Mystery, a poem for Europa. And so that's on the inside. Now, I haven't actually expanded it up to read that myself, but that is actually on the inside where it's bolted onto their electronics assembly. So this is like the access hatch that protects the electronics. Yes, Fred?
What's the object of this 6-year...
The Europa Clipper mission?
Yeah.
Effectively to look for whether the conditions for life, as we know it, are present on Europa, because it has what's believed to be a large ocean of water beneath an ice layer. And you can see the size of the craft here relative to the Technician. Now, this is just the bits and pieces of it, because it also has these extremely large solar panels on it. So the thing overall, when it's unfurled, is about 31 metres long by 18 metres wide, and they said it's about the same size as a basketball court, and it's the largest spacecraft that NASA has actually sent out. And of course, why it needs those very large solar panels is because the light level out of Jupiter is incredibly small, and so they've obviously gone for this as an option rather than sending like the radioisotope batteries that they have done in some of the earlier missions, like the Voyagers that went out to the furthest reaches of our solar system. So it's on its way. Now, the other thing I'd like to show here is something that Guido extracted from the new all-sky camera, which is bolted on the top of the observatory just down the hill here. And you can see it's a full fisheye view lens from horizon to horizon. You've got east over here, west down the bottom there, north towards Melbourne, which is over in that direction, and south over here. And you'll notice a couple of things. One, that's the moon, and I'll play this in a moment. It goes for about a minute and a half. You'll notice the moon slowly move across the sky and set in the west, as you'd expect. The sun has already set, so you're sort of seeing a bit of twilight down here on what the camera's seeing. You'll notice a fair bit of light pollution from Melbourne over on the right-hand side, and then you'll see it's caught at least 2 or 3 instances of the aurora australis pushing up in the sky. So this was last Thursday and Friday morning. So Friday morning just before dawn, it was quite a good display. Now, a bit hard to see here, but there's a number here that will become visible in a moment, which is the KP index. I assume that's the planetary KP index, and when that gets larger, you're more likely to see an aurora appear in the sky. So if you keep watching that number, when it goes up, it will correlate with an aurora appearing here. And so what I'll do is I'll just play this one, and there's a bit of music called So Excited. So as you see that, the aurora extended up 2 to 3 times the height of the trees that are just down there to the south, and they're pretty tall trees, so that would have been very high up in the sky from here. And you can see that live on the MPAS website. Guido has put it up there, and you can see it's every 2 minutes, I think it's refreshed. You can see what the current conditions are here at the Briars, so that if you're wondering about whether to come down, you can see exactly how cloudy it is and what it looks like before coming. So tonight, number one, I'll show over here that my name and Roz's name are on the Europa Clipper, and I'm sure quite a few other members may have submitted their name as well. Yeah, Lee as well, and Phil, yep, have put their name on the Europa Clipper, and they're amongst the 2.6 million that are going to go off to Europa. Welcome to any new members. Since the last meeting, we've had one family member, Natalie Hampson, and the family, and I don't think Natalie's here tonight, so we'll skip over at that. Events, I'll look quickly at the past events and coming events, and then I'll throw over to hopefully Chris. We can get him online. Yep, okay, fantastic. Then on to Sky for the Month with Guido, and then we'll look at the art and science of the images that come from the Webb Space Telescope from a couple of the people who are actually responsible for producing those images that are released to the public. They get the raw black and white ones from the Webb telescope, and they tell you a bit about how they turn that into the spectacular images that are then subsequently released. Then after we've had a bit of a tea break, I'll show about 10 minutes of all about the number Googol, and that's the correct the correct spelling of Google, not the way the web search engine is spelt, but what a Googol is, what a Googolplex is, and how they relate to the size of the universe, and also the number pi, which is associated with obviously circles. And then we'll close with the SpaceX Starship 5 launch, the one that was caught by the so-called chopsticks method, and just showing at least the part up to where it's caught. So I didn't include the much longer part of the upper stage that went for about another hour around the Earth before dropping into the Indian Ocean. They didn't try to recover it this time, and it went kaboom at the end when it submerged in the water. But even that kaboom was sort of hailed as a bit of a success. All right, recent events. We've had the cosmology discussion group here at the Briars on the 21st September, which is a Saturday, and the Working Bee and Members Barbecue. Phil Peters and Greg Walton have been busy on a few things here on the site. Greg fixed up an issue with the ride-on mower that we have. It required some significant welding repair to get it going. Phil has been building the gate, which indeed could be used tonight if you wished, and the pathway that leads round to the toilets next door, the new toilets within the Echo Centre. He's also painted the floor out the back, and I do like the colour. And you'll notice over here he managed to capture, slightly out of focus in the picture that I got, but managed to capture something sitting on top of the all-sky camera, which, as you can see, is a kookaburra, and that is the all-sky camera there. So if you look at the all-sky camera on the website and you don't see very much, it could very well be that you've got a bird sitting on it at some stage as well, but that was very funny to see that there. Our committee meeting, we talked about the events, at least the first cut of them for 2025, for putting together the calendar. We've also got a calendar underway, as in the calendar that we ordinarily would buy from a third party, but this is instead being put together by MPAS using member images instead, and with a bit of luck we'll have that there well and truly in time before Christmas. We talked about the new life members, and also the buy, sell and swap meet that we'll do with the TLD next year, which I think from memory was in March. So we'll be having one of those at the same time as the TLD. 4th of October was the public night here at the Briars. It was very cloudy, but nevertheless they did get to see something, and Trevor gave the talk at that one. Now coming up, we've got a few things. One, this Saturday we've got the Telescope Learning Day here at the Briars, and that starts at 4 o'clock. It's fully booked out. Members are welcome to come along, but we would appreciate at least knowing you're coming so that we can cater accordingly. Committee meeting is going to be next Tuesday by Zoom, and any financial members is able to dial into that as well. Then we got the last Scouts Cubs and Guides night here at the Briars on the 25th of October, and that one is pretty well booked at the moment, so 52 booked so far. And Catherine and I will be talking at that one. Then Manfred will talk at the public night on the 1st of November, and we've potentially got a stargazing night for Narrawarren North Cubs. Don't know whether they want to come here or we go to them. That's yet to be established, but I just sort of put that in there as a bit of a holder of the date so that you're aware of the date. And the next monthly meeting's the 20th of November. Now, any moment now, we should be getting the Astronomy 2025s in. We're hoping they'll come in either tomorrow or on Friday before the TLD, but fingers crossed. They're coming from Sydney, it turns out, now. And also mentioning the 7th of December coming up, we've got the Christmas concert, which will be here in the Briars with the Southern Peninsula Concert Band. And with that, we'll see how the technology goes.
Welcome to AstroMofo number 18. So the monthly photo challenge for members, and the last challenge was to get some images of galaxies. So the opening image that we have here is by Nerida Langcake with her Samsung S20 Note Ultra, and it's of the Large Magellanic Cloud above Lake Nilakudi, where Nerida went for a star party recently. So the galactic challenge was completed by Nerida Langcake, Kelly Clitheroe, Nick Kaxaris, Guido Tack, Dave Rolfe, and Chris Kostokanellis, myself. And what we've got here is Guido's image of NGC 55, or the String of Pearls galaxy in Sculptor. And this one here is an elongated barred spiral, which is viewed edge-on from where we are, and it's around about 7 million light years away. So it's a really nice image of that by Guido. And we also have one by Dave of the same thing, imaged using different type of equipment. So Guido's was with a colour camera. Dave's here is with a monochrome camera and hydrogen, sulfur, and oxygen filters. So that is the String of Pearls galaxy. Next, we've got a couple of images by me, imaged from Heathcote here, where I am at the moment. So we've got the Small Magellanic Cloud on the left and the Large Magellanic Cloud on the right. Both of these were imaged with my ASI 294 camera, and just a basic lens, a Canon 75 to 300 millimeter zoom lens at about 100 millimeters, and my little AZ GTI tracker. So the Small Magellanic Cloud, around about 70 minutes of exposure, and the Large Magellanic Cloud, about 170 minutes. So these are two neighbouring galaxies to us, around about 200,000 light years away for the Small Magellanic Cloud, and about 160,000 light years for the Large Magellanic Cloud. So they're closer to each other than they are to us. And 47 Tucana, which we see next to the Small Magellanic Cloud, the globular cluster, that's only about 15,000 light years away, so very much a foreground image. And these two galaxies are thought to be getting pulled apart and distorted by their gravitational interaction with each other, as well as the interaction with the Milky Way too. So that's those ones there. Okay, so these are images by Kelly Clitheroe with her refractor, NGC 247 and 253. NGC 300 and 1365. So these are mostly barred spiral or spiral galaxies, generally around about 11 million light years away for these ones. The furthest one is 1365, which is also known as the Propeller Galaxy. That one is the most distant. That's actually 74 million light years away. And when you do image that, it does look much smaller on the image compared to these other galaxies. So some really nice images there from Kelly. And also with this, these ones are with the C stub. So we've got M33, M31 Andromeda, that image has also got M32 on the top right, which is another dwarf galaxy orbiting Andromeda, and M110 on the bottom left as well. And also then on the right we have M83. So M83 is also known as the Southern Pinwheel, which is in Hydra. Andromeda is the galaxy that is going to merge with the Milky Way in about 4 or 5 billion years. And I'm not sure if we've started a countdown clock for that yet. Triangulum is the closest of the lot. That's only about 2.73 million light years away, which is, sort of close-ish. And is the third largest galaxy in the local group, with Andromeda and the Milky Way being the two which are larger than. So thank you very much, Kelly, for these images. We also have a couple of small and large Magellanic Cloud images from Kelly as well. On the left, we've got NGC 292, or the Small Magellanic Cloud, and that's picking up quite a bit of nebulosity around there. So that's with a 70mm scope, quite a wide field telescope, which gets a fair bit of the Small Magellanic Cloud there, and narrow band filters. Monochrome camera, so it's an RGB image. And then on the left, we've got the tarantula in the Large Magellanic Cloud with a 107mm refractor as well. So thank you, Kelly. Next, we've got some photos from Nicoxaris, Centaurus A, or the Hamburger Galaxy, which is around about 12 million light years away. And this is thought to be a spiral galaxy undergoing a collision with an elliptical galaxy, giving it that distinct sort of look. NGC 6744 is another really beautiful spiral, which is thought to be what the Milky Way looks like if you were to look on it face down. So it's thought of as a Milky Way mimic, and that's around about 24 million light years away. So, we're looking at distant objects and far away old light coming to us and creating these images. Then we've got a few, again, large and small Magellanic Cloud objects from Nick, the Tarantula Nebula, and quite a wide view image of the Tarantula Nebula there from a 300mm focal length scope, the FRA 300. So it's catching quite a large view of that section of the Large Magellanic Cloud. And then on the right, we've got a combination of wide and narrow field of view images. So the wide field of view images with an FRA 300, and Nick's combined that with images from his 130mm telescope to give detail of some of the areas in that. So the wide field shot with a smaller telescope and importing more detail from the larger scope into the image to really show a bit more detail in it. And then another couple, closer one of the Tarantula with a 130mm refractor, and NGC 292 in the Small Magellanic Cloud as well. So even though these things are fairly far away, we're able to pick out little nebulas and clusters and things like that within them as well with moderate telescopes. Okay, our next challenge will be the Comet 2023A3 Tsuchinshan Atlas. So this is appearing now in the western sky, just above the horizon when the sun set. It's still pretty difficult to see at the moment, but as the days go on and the weeks go on, it will be increasing its separation from the sun. So over the next couple of weeks, we should be able to get some good imaging on it, looking west just after sunset, sort of just below to the north of Venus, I think, is generally where it'll appear. It's just in the western skies there. So that is our next challenge, and looking forward to seeing some images of that. So also, if you already have images of the comet, and I've picked a few of them off Facebook and the socials, send those as well, because we'll show them how it was before it went around the sun when it was up in the morning, and also after it's come around the sun when it's visible in the evening. So yes, if you've got before and after shots, send them all in for the MoFo challenge. And that is me. Is there any questions?
All right, so sky for the month for October and November 24 with the beautiful cover image by Nick Axaris. So let's have a look at the solar system first. So we can see the Earth over here, and then we can see that we're catching up with Mars now. So we're heading towards opposition for Mars, and we can see that Venus and Mercury are both over there in the sky. And let's have a look at how that changes between basically today and in a month's time. So we can see the inner planets moving a bit faster than us and catching up. And again, we are catching up with Mars over the next few months or so. And then when we zoom out a bit from here, I think this should be zooming out. You can see that Saturn is now past opposition, so we're a little bit ahead of Saturn, and Neptune and Saturn are basically in the same part of the sky in this direction, and then Jupiter and Uranus are in the other direction here. So whenever you look kind of this way from Earth, right, that's more towards the night, and whenever you look this way from Earth, that's earlier. So Saturn now rises a lot earlier in the evening already. Jupiter still a little bit later. We'll see that in the all sky view. So this is the sky view for the 1st of November. And we have sunset, I think around 7 p.m., something like that, around 8 p.m. already on 1st of November. And then we can see Mercury and Venus in the evening twilight there. Venus, a very bright evening object at the moment, right? Very clearly visible. I think you can't miss it, and a really good way for finding the comet. So Saturn is visible all night. It's just past opposition, but yeah, it'll be pretty high already at sunset, and Neptune right next door. And you can see here that, well, that's Venus in the west, and that's the comet here, a bit towards the north from Venus and a bit lower in the sky. So this is for the 1st of November. At the moment, the comet is still quite a bit lower on the horizon, so much closer to the sun. I think I'll have a closer view of the comet a little bit later. So around 10 p.m. at night, the sky looks like this. So we have like the bright stars here basically forming a line from the southeast to the northwest. So Canopus, Achernar, Fomalhaut, and then actually Altair kind of also almost in a line there. And we can see Orion rising in the east now around 10 p.m. or so. And the main constellations, well, we have Sculptor right overhead, and we can see Scorpius now setting quite early, and yeah, Orion is just coming into view here in the east around 10 p.m. So if we fast forward a little bit more and see where the other planets are, so there's Uranus and Jupiter rising right now, so now before midnight. So Jupiter is definitely becoming a bit more visible during the evening now. And so Uranus is heading for opposition on the 17th of November. Jupiter will be at opposition in December. And Mars now rising around 2 a.m. Of course, all of this is now after daylight saving, so that's why there's actually another hour difference there if you think about it in like real time. But yeah, rising around 2 a.m. now. And then going towards the morning, of course, sunrise a bit earlier now as well. I think around 6 a.m. And then for the next month, we'll have the full moon on the 17th of October, so that's tomorrow. And that's a super moon, so it's at its closest point in its orbit at the same time that it's the full moon. We have a new moon on the 1st of November, and then another full moon on the 16th of November. And again, that will also be a super moon. So we've had, I think, now 3 in a row, so that were all at perigee when the moon was full. And yeah, sunrise around 6 a.m. All right, just a quick look at the apparent sizes of the planets. So Mars and Jupiter are getting bigger because we are heading towards them. Saturn is still a really good size to observe at the moment. So we should get some nice views of Jupiter over the next few months, and then Mars will be at opposition in early 25. So also still about to get a little bit bigger from here. So let's have a look at the comets. I mean, so this is really the one that everybody's interested in at the moment. That's the only one that's brighter than magnitude 10 at the moment. It's setting just after sunset, as we've seen. And it's predicted to fade to magnitude 10 by the end of November. So at the moment, it's much brighter than that. I'm not sure what the exact brightness is at the moment, but I saw some like visual estimates of around magnitude 2 or 3 or so. So that will be a lot brighter than what it will be by the end of November. And this is now moving 1 day for each step. Right, so this is 25th of 28th of 29th, 30th of October. So you can see that it's actually rising a bit higher. This is always at 8:30 p.m. So we should get a much better view, but it's always kind of to the right and a bit lower than Venus. So that's a good way of finding it because Venus is so obvious in the sky. Now from the end of this month, the other problem is that the sun will set later and later. So even though it's getting a bit higher in the sky, the sun will also still be a bit higher in the sky at 8:30 p.m. So we're not getting that much of an advantage there. But yeah, there should be a few really good opportunities. And the images I've seen over the last few days looked really impressive with a very long tail. And so yeah, hopefully we'll get some nice views of that. We have a few meteor showers, so these are actually the same that I showed last month, so the Southern Taurids and the Orionids, because they're still active right now and into the next month. So Southern Taurids peaking around the 5th of November and Orionids peaking around the 21st of October, so next week. But both of them, well, especially the Orionids, will be affected by the moon because we're basically at full moon right now. The Southern Taurids should be okay because you can view them after the moon has set around 1 a.m. And then we also have the Northern Taurids starting basically next week until the mid of December, and the Leonids from the 6th of November till the 30th of November. But both of them will be affected really heavily by the full moon around the time of the peak. So not sure that that's going to be that interesting this year. And that's really all for this month. So as always, the sources were Stellarium for the all-sky view, NASA Eyes on the Solar System for the overview, and then Astronomy 2024 for all of the data. Any questions? All right, thanks.
The talk goes for just over an hour, and it's all about the art and science of the Webb Space Telescope's imagery, and shown there are the two speakers, Alyssa Pagan and Joe DePasquale. His name I actually noticed today was on one of the images that they'd done for Uranus that was being shown online, and so I recognised the name straight away. So this is a public lecture given by the Space Telescope Science Institute, And that's the one that we had a visitor from several years ago came to actually speak to us here at the Briars. And these are two very lucky people that have qualifications in arts and science, and they consider it to be a dream job that any astrophotographer who likes image processing would go for. So this public lecture now is getting on for almost 2 years old, but nevertheless very, very relevant today, and it's hosted by Dr. Frank Summers, an astrophysicist at the STSI.
Tonight's talk, the art and science of Webb imagery. Speakers tonight are my colleagues, Alyssa Pagan and Joseph DePasquale. And I'm so glad they came on here to give this talk. Actually, I had to bribe them because, you know, they've been doing so many talks these days. They're like, oh, another talk, Frank? No, but I guilted them into it, okay? Alyssa came to us in October of 2019, and actually she joined just like 4 months before we all were sent home for the pandemic. So a good amount of her early time, she was working from home without the benefits of actually being in the office. She's back in the office now, though, and she got her dual degrees. She got a degree from Towson University in art and design. And then she went back for another bachelor's degree in astronomy at the University of Maryland. So she's got the art degree and she's got the science degree. How perfect for the job she's doing. And then she worked at the University of Maryland as a TA for a little while she says she repeatedly applied at Space Telescope until we finally accepted her. And we were very lucky to have her. Joe, on the other hand, grew up in Philadelphia. He did his undergraduate degree at Villanova in astronomy and astrophysics. And then Joe went up to the Harvard-Smithsonian Center for Astrophysics up in Boston. And he spent 8 years working as a data processor, okay, doing the actual work with all the data for the scientists that were working there. And then he switched to public outreach and became an image processor for the Chandra X-ray Observatory, and I assume other missions that they run out of there. He did so fantastic of a job up at Chandra that we stole him away, and we pulled him here back in 2017. So he's been with us for like almost 6 years now. All right, and so this is our dynamic duo of image processing.
Hi, everyone. Thank you so much, Frank, for that introduction, and thanks for joining us, everyone. Let me get my slides up here. Anyways, thanks, everyone. I am Alyssa Pagan, as Frank mentioned, and I work with Joe DePasquale, and we process the imagery for Webb. So we take astronomical data from Webb and Hubble and other observatories and create color imagery, and we do that to support our news releases, our outreach products, and other educational resources. So that's what we do. But before I jump too far into the process of how we do this, why do we even care about infrared light? Why do we study it? And why do we need a space telescope like Webb to look at infrared light? So you might be familiar with the electromagnetic spectrum. Of course, we're all familiar with visible light, and that's just a very specific part of the spectrum that we can see with our own eyes. But as you can see, it's a very, very tiny part of the spectrum. On the right, we have the shorter wavelengths, so the higher energy wavelengths, like the X-rays and the gamma rays. And on the left, we have the longer wavelengths, so the lower energy wavelengths, the radio, the microwaves. And so if we just studied what we saw, then we'd be missing all this stuff in understanding our universe and space, and in particular, infrared. And of course, it's not just about studying it, but we actually use light to transfer information. So if we didn't actually know about this, then we wouldn't be able to sort of text our friends or turn on the TV or, you know, listen to the radio. So it's very important. And we'll focus on infrared, which is really important for understanding astronomy, objects in general. And so what exactly is infrared light? So we feel it as heat. And so you can kind of think of it, if you've ever seen the movie Predator, he has infrared vision. So he's looking for the prey, he's hunting them down, he can see them like in a bush. And so that's how it works. And so on the left, we have an image showing that. We got a fellow here, he's sticking his hand in this trash bag, which is opaque to us in visible light. We can't see the hand. But if we take an infrared camera, all of a sudden we can see that hand is emitting the heat, and we can capture it. And so the brighter regions that are hotter are showing up in sort of this white yellow, and then the cooler regions are this bluer purpler color. So And it works, that mechanism works the same when we're looking at space, because we can look using infrared light to see through dust and gas, whether that's to see sort of the stars that are hidden within the dust or to see behind the dust, to see sort of these young galaxies. And well, that goes into this part as well. Why infrared light is important is because it helps us to see farther into the past. And this is because of something called cosmological redshift. And all that means that space is expanding. And as space expands, light that's traveling through space also extends or stretches. So if something's emitting far away from us invisible light, by the time it gets to us, the wavelength has been stretched so much, redshifted, so that we see it in infrared light. Well, we can't see it, but that's why we need these telescopes to be able to see it. And that way we're seeing sort of the first galaxies and the first stars that have formed. So it's a very powerful tool. And the reason why it needs to be in space, of course, is because the atmosphere primarily absorbs all this infrared light. So we need it to be above the atmosphere so it doesn't interfere. And also we need it to be very cold because it is heat. So we don't want sort of extra signal coming from the heat of the instruments, which is why Webb has a sun shield, and it's why it's located where it is. And that's kind of to go full circle at the importance of being able to see in all these different wavelengths of light, just like we have Hubble that sees a little bit in the visible, well, a lot in the visible, a little bit in the infrared, a little bit into the UV. Webb sees farther into the infrared. And that's the same reason why we have medical equipment too that sees in different wavelengths to tell us different things about our body. For instance, we use X-rays to see our bones versus like MRIs to see our soft tissues using radio wavelengths. So it's all very important to our understanding. Another question that comes up often when people are looking at these images is, are they real? And then what goes along with this often is this how it would look like if we could actually go there? So the first question I can answer very easily and say it's 100% real in that it's real data. It's real astronomical data that is being collected by these telescopes. It's just light that we cannot see or measure with our own eyes. So would it look like there if we could go there? Well, not quite, because again, our eyes are not as sensitive as these telescopes. And of course, we cannot see in infrared, but it's a huge tool. And just because we wouldn't see it this way doesn't mean the universe doesn't exist that way. We're getting more information. And so a nice way to also sort of explore this a little bit further is to look at a parallel into a different science field, in this case, microbiology. And like astronomy, microbiology uses advanced instruments in order to help our understanding, to see things that we can't see with our own eyes. In the case of microbiology, we use microscopes. And then, of course, for astronomy, we use telescopes. So on the left here, we have this black and white image of the coronavirus. This is how it appears through an electron microscope. And so we're getting information here, but it's not quite as interesting or evocative as sort of this image you see on the right. This is actually a rendering that was produced by the CDC. And we're actually seeing, using the color to sort of separate these different structures, the different proteins that are actually existing. And this is very similar to how astronomy works, in which we are using color to showcase different structures as well. But in the case of astronomy, these structures and colors aren't arbitrary. They actually have physical meaning. And we'll get into what the wavelengths mean and why we prescribe the colors that we do a little bit further on. But as you can see, when we're combining all these wavelengths together, we're getting that full color image. We're seeing all these different structures that are contrasted by the color, which are saying different things that are actually physically happening in this particular image. And then also, why do we make color images in the first place? Like, it's really fun and it's really nice to look at. But of course, I kind of mentioned it before, is that it's really important to be able to see the data to visualize it. So numbers are great for data analysis and science and research, but just to get like a broad overview understanding, big picture understanding, it's helpful to see all the data sort of at once in a color image. And then of course, we want to illustrate the scientific discoveries and the concepts, because science is for everyone. What we find out is something that we want to share, and we want it to be digestible. We don't want scientific literacy to limit sort of what people get from these discoveries. We want to make it, accessible. And that sort of ties into engaging the public. We want images that are compelling, that inspire, that make you want to get interested or involved in astronomy, and maybe inspire a next generation of engineers or image processors or, whatever. And so those are the goals that we have in mind when we're processing these images, and it affects sort of our decisions that we make as we go along. Okay, so now let's actually get to sort of a general idea of how we process web data. And so the start is something we call image stretching. So it might come as a surprise to you that these images don't start off in color. They actually start off in black and white. And so this is actually one image of the Webb deep field taken through one specific filter or one specific wavelength range of light, the 2.7 micron filter. But as you can see, it looks very dark. It doesn't look like there's anything there, but there is. It's just because these telescopes are so sensitive that we have to actually scale the brightness values in order to show them or display them on our screens. So you can see here, there's all this data here, but it's all kind of locked up in the black point. So this is a histogram, and this represents the brightness distribution, or the values here, or the pixel values distribution. And you can see that they're all kind of pushed to the black end, but we want to literally stretch this histogram out. We want to distribute it so that we can actually see the details that are hidden in the dark end. So a nice way to kind of look at this is like a simpler example, and we have this 4-value parrot here. We have dark gray, we have black, light gray, and white. And we have this distribution of these 4 pixel values here. Now, what if we wanted to scale the brightness values of this image, or stretch it, so to speak? So on the left here, our first example, we haven't done anything. This is just linear, one-to-one, no transformation. Now on the middle part, we have scaled the brightness values, but now you can see that while we're trying to bring out this darker gray, we end up completely losing the brightest values. So we can't differentiate between these pixels, which is not good, because then we're losing information. And so what we end up doing, and this is the stretch that we want to do for astronomy, is we want to do what we call a nonlinear stretch. And that just means performing a transformation that helps to emphasize these darker regions, bringing out those details in sort of the parrot here, but we're not losing those values on the brightest end. And so we can see another example with this image of the Webb deep field. And this is what we call the linear stretch. This is something that we don't want to do because, as you can see, even though we're bringing out those faint structures in the background, we're completely saturating these regions. It's too bright. We've lost information here. And you can kind of see that here in this histogram because it's been cut off. It's been clipped. So that's information that we can't get back if we continue on. So that's why it's so important to apply what we call a nonlinear stretch. So we're preserving the highlights, we're bringing out these features. You can kind of think of it as bringing out those midtones, and we are stretching out this histogram across this range of values. So we get a really nice contrast-driven image. So let's look at that with an example of the Carina Nebula. So for the Carina Nebula, we have 6 different filters here, or 6 different specific wavelength ranges of light that we collected. And here they are non-stretched, so this is linear. We haven't done anything. This is straight from the telescope. But for all the filters, we have to do that stretching. We have to scale the brightness values. And so that's what we do here. You can see like it comes to life. All of a sudden you see all this detail and structure and information. And that's exactly what you want to do. Okay, and now we get to the second step after this, which is the chromatic color, or prescribing the color. So I kind of mentioned this already, that these images that we get start off in black and white. And the way we prescribe color is we collect specific wavelengths of light through this filter wheel. And so this is actually a video of the mid-infrared instrument, the MIRI instrument, which is collecting the light, redirecting it through this filter wheel. The filter wheel can move, and then we can get different specific wavelength ranges of light. And then it's redirected to the detector, so our camera. And then it gets sent back to us. Now, how do we prescribe color? So we see visible light as the shorter wavelengths being the bluer color and the longer wavelengths being the redder color. And so that's the relationship that exists with visible light. So we extend that relationship into the infrared, essentially. So even though we can't see an infrared, we can use that relationship and apply it to the infrared. So in essence, you're taking the infrared wavelengths and shifting it into a visible color space. So now your shortest wavelength in infrared is your bluer color, and etc. So you can see that's what we do. That's how we apply color in chromatic order, where our shortest wavelength filter here is prescribed blue and so on. So cyan, green, orange, red, and then yellow, which seems okay. We got an outlier here because, right, this should be red. But the reason why we do this, we're not actually breaking any conventions here. This little guy on the right is actually very, very hot hydrogen gas, and it's a very specific filter range. And it actually gets captured in another filter, this 2.12 micron filter. And so if we switch it out, we're not breaking any rules here. And the reason why it's important to actually designate this yellow rather than red is because it's a really important feature that's showing you where these really hot young stars are embedded in this dust. And if we just prescribe it red, we're losing all that information there. And that's the whole point, is we want to showcase the science and the astronomy and the, you know, all this really cool information while making it compelling. Okay, so after we have performed the stretching and we're prescribing colors, we want to do one thing on each filter before we continue. And that's dealing with stuff with like artifacts. And artifacts are just intrinsic to the detector, the telescope itself and the calibration and all of it. So it's something that you wouldn't actually see if you were there. So things like readout noise from the electronics, or you have these sort of dark centers of stars, those are introduced by the calibration pipeline. So all this data gets cleaned up, and because these stars are saturated, they get replaced with null values, because it's just a warning to the scientists that you can't perform any sort of photometry, you can't perform any sort of analysis on this because it is no longer reliable. So that's just sort of, that's why that is there. But we have to remove those because, of course, we're not looking at the sky and seeing these black in the center of stars. And we also have these striations again, which is from the electronic readout noise. So we have to do things to remove this. And we have a lot of algorithms to do this, but this is just some of the things that we end up doing in sort of photo editing software, is removing those bands and replacing that area of the dark cores with the nearest neighbor. Okay, so this is our first initial color composite. After we've done the stretching and prescribed all the colors, this is what we initially get when we combine them additively together. And so this is, there's no one point that it turns into a subjective from the objective. We're always sort of weighing the art and science elements as we go along and thinking of the story we're trying to tell, the science story we're trying to tell. This is sort of the first phase of that. Now, that being said, there still are artistic principles or aesthetic principles that we're thinking of all the time and that we're applying. And things like clarity, color, composition, things again that help tell the science story. In fact, there's decisions that we've already made that are aesthetic decisions. Things like I was talking about the artifacts that we removed, but there's actually an artifact in here that remains, and that's what we call the diffraction spikes. So this 8-spike star, we keep that in there. And why do we do that? Well, there's a little bit of a whimsicality there. It's sort of like the twinkling star is just sort of what you think of space. So when you think of a space image, you think of these twinkling stars. And so that's sort of the convention there. But also it acts as like a signature to Webb, because the diffraction spikes come from the light interacting with the hexagonal mirror of Webb, and also the 2 struts that are holding up the secondary mirror. So that's why you get these spikes. And so we keep them in there so you know, like, oh, we're looking at Webb. Also, it'd be really hard to remove them. It would take a long time. We do have algorithms in place to sort of replace those areas with samples of data. But the better way to do that would actually be to rotate the telescope, get another exposure of it, and fill that data in over the diffraction spikes or where they overlap. But that costs a lot of money, and there's a lot of competition for Webb time. So it's not the most feasible thing to do. Also, a decision that we've already made that you might have not thought about, you've probably seen this image, Carina Nebula, and if you have, it's been primarily in this orientation, even though the Northup convention for astronomers is the orientation on the right. Now, why is that? So there's no true north-up, so it could be really anything. It's just a convention that astronomers use, but it was a choice to change the orientation. And that choice is important because the one on the right feels a little bit unbalanced, unstable. And also, if we crop this down, we're going to lose a lot of real estate. And of course, we want to showcase all the details in the data that we got because it took a lot of time to get it. So we're thinking about that. And we're also thinking about how does this provide context? So this helps us feel like this is a landscape. This feels more familiar, something we might have seen, something that we can draw a parallel to. So in the case of this Carina Nebula, these mountainous regions, they're being eroded by these hot stars. And that's similar to what we'd see, you know, on Earth, where we're looking at mountain ranges that are being eroded by weathering or natural forces. So that parallel helps with the story and the understanding of what's actually happening in this image, besides just making it feel a little bit more stable, like more appropriately weighted, and helps your eye move across the image. Okay, so let's go back to our initial color composite. This is where we're kind of looking at this more as a photographer would. So we're thinking of sort of the white balancing. We're thinking about color balancing. So we use the center of the stars for our white references in this particular case. And normally we would neutralize the background, make sure that we have equal number of our red, green, and blue values, because that background should be very, very dark gray or almost black. But in the case of nebulae, we don't really have a region to use as that reference because there actually is some dust. So there is a little bit of, or I should say, there's some gas back here. So that's not true, you know, dark sky. And so there is a little bit of by eye that we have to do, but it is a very iterative process, and it's one that we do with the scientists as well. So starting from this phase, I actually end up shifting this image a little bit closer to the blue part of the spectrum. Now, all the relationships between the colors remain the same. They're just slightly shifted to really bring out these two different processes at work here. We have the mountain range on the bottom, which is just the very dense dust. And then on top, we have the hot gas. And sort of that complementary nature of that orangey dune-like scene with the sky scene feels a little bit more familiar and also helps with that contrast. And of course, I want to bring out these features even more because that's, you know, we got all of this data and these different filters that are showing us different things. We really want to bring out the contrast and the color separation here. Now, this, I went a little too far here, so I have to take it back. And that happens sometimes. You work on an image for a while and then you get so, you know, wrapped up in the pixels and bringing out all that detail that you kind of have to take a step back and be like, oh, you know, that doesn't seem natural anymore. So you kind of have to take it back. And at this stage, again, I'm working with the scientists, and this region we have here is sort of this blue gas that's sort of coming through this mountainous region, and it seems to be overshadowing it, obscuring it. And this is very real. This exists. But speaking with the scientists, they felt like it took away from the 3D nature of the dust and the structure. So we want to go back in there and really enforce that dust 3D landscape. So that's what you can see here. It goes a little fast, but you can see that we get a little bit more of the structure back in here. And we've toned things down a little bit. And then in the end, this is what we are left with, the final image. And there's a lot of ways to sort of approach an object, and different objects will be processed differently. And they'll also be processed differently by different people. And so I'll let Joe get into that a little bit more in the next presentation.
Thanks, Alyssa. I'm going to pick up from here. So let me share my screen, get the slides going. Okay, so I am going to continue talking about the Carina Nebula image, but before I do, I just noticed that Alyssa was talking about the 8-pointed stars on Webb, and I thought we could explore a little bit about why they appear that way. It actually has to do with the optical system of the telescope. In a system like this, every hard edge imparts a diffraction pattern onto light sources, right? So a point source star is going to interact with the hard edges all along the mirrors. So all 18 hexagonal segments are going to contribute something to the final appearance of the star. In addition to that, we have these green lines representing the diffraction that's imparted by the support struts that hold up the secondary mirror. And so when everything comes to focus at the detector, you get this pattern, which we see in every bright star that Webb observes. So that is the origin, sort of, you know, generally quickly summarizing where that comes from. That is the origin of Webb's unique diffractions pattern. Now, jumping back into the Carina Nebula, what I'd like to do is talk about the MIRI observations of this. Remember, Alyssa had discussed a little bit about the mid-infrared instrument. We took MIRI data of this same region. It's a smaller field of view, so it actually takes up this region here. But the origin of the appearance of this image is actually an interesting story. Let's see. Yes, so it's the mid-infrared instrument. And remember, Alyssa had showed this movie. This is actually the final frame of that movie that just shows you there's, the pick-off mirror, then the detector at the bottom, and the filter wheel, which is where all the colors come from. So this is just to sort of ground you in what MIRI is and where that data is coming from. Now, MIRI is observing in the longer infrared wavelengths. And so if we were to combine the data together of NIRCam and MIRI, according to the chromatic principles that Alyssa has laid out, you would expect to see something like this, where the blues and the teals and maybe the greens would be confined to the NIRCam regime of the image. And then as you move into longer wavelengths of the MIRI, we would have yellows, oranges, and reds. It turns out if you apply that process to the data, you get an image that looks more like this, which when I first put this together, I wondered how we were going to deal with this. It's not a very aesthetically pleasing image. The purple sky, the green clouds. It's interesting that astrophysically speaking, most of the stars in this image appear in the short wavelength infrared bands. And so they don't appear in the mid-infrared. And so you end up getting a lot of blue stars that are just pure blue, which looks very unnatural in the composite color image. So the next step for me, the next logical step was to say, well, okay, this looks kind of strange. What happens if we just make an image in the MIRI wavelengths alone? And what do we get from that? So shifting this just to MIRI and applying the chromatic ordering to the MIRI wavelengths, what do we see? We see this. And when I put this together, I thought, well, this is actually a really interesting image. It's very evocative. It's very different from what we saw with NIRCam. In fact, it actually reminded me of Monet's Rouen Cathedral series of paintings. Monet went to this area of France and painted the Rouen Cathedral over 30 times at different times of day, trying to capture the essence of the atmosphere, of the lighting, of the atmosphere, whether it was morning or evening or mid-afternoon, the effects of the environment on the scene itself. And you get 30 very different looking paintings, even though it's the same object. So that if this image brought that to my mind as I was working on it. And so then I thought, well, okay, we have this beautiful image from MIRI. We also have this beautiful image from NIRCam. Is there a way that we can combine them together that emphasizes both the astronomy, the astrophysics of what's happening, but also emphasizes the beauty that each of these instruments provides in this scene? And so we came up with this idea of interleaving the short wavelengths, the middle wavelengths, and the long wavelengths of each camera together, right? So now we have what we call near MIRI cam, where the short wavelengths of NIRCam and MIRI are assigned blue, and then we go to green and to red. And that was how we came up with this final version of the image here, which, aesthetically speaking, we have stars with white cores in them, which looks more natural. But astrophysically speaking, it's still astrophysically relevant, right? The young stars, the stars that are embedded in dust, they still appear dusty and red because they show up red in both NIRCam and MIRI. And it actually gives us more information than either one of them alone. NIRCam gives us all of the stars in the background. MIRI gives us a deeper, we penetrate deeper into these clouds to be able to see these young stars in the process of forming with their jets shooting out in different directions. Okay, so that is the story of the near MIRI cam. And now I would like to shift focus to the Tarantula Nebula. This is one of my favorite images of the early release observations. This one was actually the first image, the first data to come down from the telescope. And of course, this is that image. And when this was released, it was actually compared to like old masters Renaissance era paintings, right? Like Caravaggio. So I did a little research and I found a painting that I thought kind of captures the quality and the essence of this. And that is Caravaggio's painting of Judith beheading Holofernes, which, despite its macabre nature, it's actually the colors here and the quality of the light really echoes what I think I see in the Tarantula Nebula. And just keep that painting in mind. It'll come back later. I do want to go all the way back to the source data, though, and talk a little bit about where this came from and how we planned this observation and put it all together. So in both the cases of Carina and Tarantula, these are mosaics made up of many different images. In both cases, I believe it's 6 filters. So let's zoom in and look at the raw data that we get from the observatory. We're going to back out to the very first frame. Okay, this is when we take observations with Webb, it takes a series of exposures and it adds that together to get to the final image. So this is the first exposure. We call it a stage 0 image. So it's uncalibrated. And it's about 161 seconds of exposure time. So it's, like 2.5 minutes roughly that the observatory was just collecting photons of infrared light and creating this image. And you can see here that there's already some stars and they're saturated. And so this is actually the origins of the black holes in the centers of stars. If you have a saturated region in the very first exposure, there's no way you're going to be able to get valid information from that. So the pipeline processing will assign null values or zeros to those values, those pixels. And so you end up getting these black holes. But watch as I step through, for each exposure, one exposure on Webb is actually 8 individual of these 160-second exposures. And you can actually see the image sort of come into view with each additional exposure as I step through it. Now, this next one is going to be the next step in the calibration processing. And it's where you'll see the black holes come into play. So now we've gone from the 8 individual exposures to one calibrated image. This is called a rate image. It's actually not calibrated yet, but this is the combining all of those 8 exposures together to get the depth and the detail in a single exposure. But you can see if I bounce back and forth where you have those bright regions now, that was saturated data, that's invalid data. So it's been assigned black. Now you fill in a lot of this through using dithers, which means you just sort of move the scene around a little bit and you take multiple exposures and you build up an image that fills in all of these holes. Moving on to the next step of the calibration pipeline, we see this slight change in the appearance of the image. This is just a distortion correction. And so what that means is that the detector is maybe slightly angled. And so the light is coming in, it's not coming in exactly parallel to the detector. And so to account for that, you have to apply this distortion correction to get the proper aspect ratio for the final image. And so this would be the stage 2 calibrated image from our pipeline processing. It has been flat fielded, so it's removed a lot of the instrumental artifacts. If I go all the way back here, you can see there's actually a lot of instrumental artifacts that are present here that can be completely subtracted out of the final image. And then we'll go back to the full field. So in this case, the Tarantula Nebula image is actually, for each filter, is a combination of over 40 individual exposures. And there were 6 filters. And so we're talking about combining together over 240 individual images to make this final mosaic image. And then this is just one filter. I think we're looking at like 3.3 microns here. The final image is actually made up of all 6 filters, and that's where we get the colors from, of course. So let's break that down and take a look at that. We're only looking at 4 of the filters here. So the shortest wavelength is the 0.9 micron, the longest is 4.4. We'll take the colors out. We're sort of working backwards from the way Alyssa had demonstrated this. And in particular, I just want to draw your attention to this F335M. That is a narrower band filter than the ones that have a W next to at the end of their name. The W stands for wideband. M in this case stands for medium band, and then you've seen N as well, N is for narrow band. And that just means a filter that allows less light through. And so for the 335M, we're talking about a filter that allows light of a specific frequency, 3.35 microns, and only a little bit of that around that area gets through to the detector. To get a really clean image in just that one specific wavelength, you can actually do something called continuum subtraction. And so in this case, we subtract the 200W image from the 335 to get the bottom image here, which gives you the light of a very specific kind of light. In this case, it's a warm dust, polycyclic aromatic hydrocarbons, or PAHs. Now, coming back to our painting here, we can sort of conceptualize this continuum subtraction in an interesting way, I think. Let's take this painting and break it down into its color channels, right? Red, green, and blue. That's how we perceive light, as Alyssa alluded to earlier with the eyeball. What if we were to take just the red filter of this image and look at that? Now, seeing the backgrounds, the tapestry in the background it shines brightly in the red filter because it is a red object. Skin tones are showing up here. So skin is very bright because it has a lot of red in it. So in a composite image, there'd be a lot of red. But imagine if you wanted to just be able to see the light of blood, right? So you could continuum subtract everything but the specific wavelength of blood from the image. That's kind of what we're doing with continuum subtraction. So going back to our color images, now, if we combine all of these together, we get this image as the final version. And this is, of course, not the final version. This is what I would consider, if you're a photographer, this would be like the raw file from a camera. And this needs to be color calibrated, white balance adjusted. We do adjustments to the tonality, to the contrast to get to the final version of the image. And rather than step through all of that, I will just allow it to fade from one to the next. And then we get to the final version of the image here after all of those steps have been applied. Shifting gears to the distant universe, I'd like to talk a little bit about our image of the deep field and how that was put together. So SMAX or SMAX 0723. This was Webb's first deep field image. We saw a galaxy, definitely at least one galaxy in here that's over 13 billion light years away. So this was a really monumental image, very impactful, maybe not as aesthetically pleasing as some of the other images from the first releases, but definitely an impactful image demonstrating Webb's capabilities to see all the way into the early universe to those galaxies that formed just a couple 100 million years after the Big Bang. So this image was pulled together through 6 different filters using the NIRCam instrument. So here's each one of those individual filters shown in black and white. As we see them, it's already been stretched, according to the principles that Alyssa described in her part of the talk. So we're looking at that here. NIRCam is very capable of looking at the universe in many different colors of infrared light. So it has a lot of filters and a lot of ways to slice infrared light. In the case of the deep field image, we used this arrangement of filters, these 6 filters here. So we have a really nice broad range of infrared capabilities from NIRCam here. Having 6 filters allows us to combine the data in such a way that we can assign the colors cleanly through red, green, and blue channels using 2 filters per channel. And it really is just a linear combination, right? So the blue channel is just the 2 shortest wavelength filters added together and divided by 2. So you get an equal weighting of both of those filters. There are other ways that you could slice and dice the data to create a color image, but to me, this seems like the most straightforward and clean representation of the data. So the green channel is then the definition it's defined as the next 2 longer wavelengths combined and divided by 2. The red is the longest wavelengths. So when we do that, we get this version of the image here. And this is like the camera raw file. This needs to be color balance adjusted, white balance adjusted. And it's interesting when we're working with a deep field image, we have the opportunity to apply white balancing using the data itself. As Alyssa was saying, with the Carina image, we use the stars and the cores of stars as the white reference. For a deep field image, we can actually utilize the fact that we have plenty of galaxies in this image as our white reference. And so I have these 2 boxes here. The top long rectangular box, that defines the background region. And so that should be a region that's sort of relatively free of any part of the image, any kind of galaxy or star. We want that to be the reference for a neutral background. And so we're trying to subtract off, any excess light in any one of the filters so that we can get sort of a neutral gray as our background value. The other box you see here on the right, that is indicative of the type of galaxy that we would use as a white reference. It's a face-on spiral galaxy. And the reason that works so well as a white reference is because spiral galaxies contain all the populations of stars, from the youngest to oldest, representing all the possible colors of stars. So from blues all the way to reds. So it works really well as a white reference to use the entirety of a spiral galaxy as your white reference. When you do that, sort of everything else kind of falls into place and the colors appear more natural here. So looking at this now, I can see the background galaxies are taking on a much more red appearance, which is what we want to see. We know those distant galaxies should be showing up in the red channels because they are red shifted. The foreground galaxy cluster has taken on sort of a more white appearance as opposed to the greenish hues that we saw previously. And so the color balance here was a very important step. The other issue that we dealt with the deep field image in particular was variations in the background through each filter. And so that sort of manifests itself here as a blue box in the bottom right. And that blue box is just there because, again, this is like a mosaic. So we're combining multiple images together. And it just so happened that in some of those images, the background levels were a little higher than others. And so when you've combined them all together, you get sort of an excess of blue in one part of the image versus another. And that has to be subtracted out. That can be handled in pipeline processing before we start working with the data. But at the time we were working with the deep field data, this was soon after launch. The calibration had not been completely finished yet. And so we were working with data that was based on ground-based calibration. And of course, the observatory had been launched. It was in space. It was in a new environment. And we had to understand that calibration a little better before we could move forward. But we had to take these observations and get them out there. So we sort of had to calibrate by hand on the fly as we were going. And in the case of the deep field, it was actually a large amount of that was done sort of by eye. Here, I've isolated just the short wavelengths channel. So this is the combination of the 0.9 and the 1.5 micron data. And I used what we call curves adjustments to balance those pixel values in the boxes and try to get a uniform background throughout the image. And so now this next slide should be an animation that shows the stepping through each one of those curves adjustments. And as they're moving, you can see that the overall background is sort of unified. We're getting a much cleaner image, and the background is becoming much more clear. In the end, we have a really clean image. We have to be really careful though, because the foreground galaxy cluster here actually has the glow of very faint stars that have been sort of flung all out from around it. And that is it's a very faint signal. And so it could easily be sort of crushed in this process where, this ring of material here from these stars and this area down here, that could have easily been crushed. So I just had to keep that in mind as I was adjusting the background levels for the final version of the image. So after applying this change, we get to this version of the image. This is a little bit more uniform in its background. And at this point, there were some artifacts that had to be dealt with, cleaned up to get to the final version of the image, which we see here. And the final adjustments were some of the artifacts, cleaning up some artifacts and also getting that background down, suppressed down just a little bit to give you sort of that sense of the deep space background from which all of these galaxies are sort of popping out. And and then what I like to do with this image is actually we can compare it to some previous observations. So we'll zoom out a little bit here, and we will reference this against previous Hubble observations of the same region. Now, this is slightly unfair of a comparison because this was only 2 hours of exposure versus Webb's 12 hours. But still, it gives you a sense of the difference of what Webb and Hubble have here in looking at this version of the universe. Being able to pull out some of those really faint galaxies, only Webb can do that. Hubble is not going to be able to see the really, really distant or the really dusty galaxies, things that have been redshifted so far that they're sort of outside the range of what Hubble can see. This is the Hubble infrared image. Remember, Alyssa mentioned earlier that Hubble is capable of seeing infrared. It sees a little bit into the infrared. And so this is that view of this region of space in infrared from Hubble. And then this is the view from the previous flagship infrared observatory, the Spitzer Space Telescope. It had a much smaller mirror than Webb's, and so its resolution capabilities were much more limited. But it was able to detect, the signals of these galaxies in infrared wavelengths, similar to what Webb can see. But I really like doing this slow fade from the Spitzer to the Webb image, and you can see as the universe comes into focus here. So finally, I thought I would just like to ponder a little bit of the question of why do we do this, right? Why? I mean, Alyssa already talked a little bit about why do we study infrared light? Why do we use Webb? Why do we need Webb? But also, why do we put all this effort into creating these color images? And what is the significance of that? Now, personally, I think that these images, they speak to an innate curiosity within us to understand our place in the universe, to understand where we come from and what we're made of and where we're going. And it's really is true when you think of, as Frank was mentioning earlier, to bring this full circle, he mentioned the astronomer's periodic table, where hydrogen and helium and everything else is metals, right? And that comes from the fact that in the Big Bang, the materials that were created, or all of the material of the universe was created in the Big Bang, but only hydrogen and helium had enough time after the Big Bang and the universe cooled. We only had enough time for hydrogen and helium to form. All of the heavier elements had to form later on, millions of years later, after the first generations of stars formed and died and exploded and populated their environments with heavier elements. And so quite literally, we are star stuff, to quote Carl Sagan. We are made from the materials that were generated in those generations of stars. And we are the universe attempting to understand itself. And so, as opposed to give in to despair, when you look at an image like this and you ponder the enormity of the universe, there is a tendency I've seen, at least online, to give into despair and to think like, oh, we're so insignificant. We have no place in this universe. We're such a tiny speck. But really, these images, they give us a window into our origins. We're looking at the raw materials that make up solar systems and planets and ultimately life. And so I feel a deep sense of connection to other people through pondering the universe, through looking at these images. And I think that's an essential part of what makes them important and why we do this. To take that even further, physicist Alan Lightman provides some really good context to why it's important to observe the universe. How do we fit into that, right? In two different ways. One is, if you think about the human brain, it's made up of neurons, and there are approximately 100,000 billion neurons per human brain, right? And it just happens to be almost the same amount of stars that make up a galaxy. And so as you're walking around and you see people in the street, you can think of them as each being their own little galaxy, right? You're a galaxy among galaxies in the world. And so that provides a certain perspective, right? The other one is scale sizes. If we think about scale sizes and how do we compare to the enormity of the universe, well, if you took the average human and you were to divide them in half multiple times, how long would it take, or how many divisions would it take to get to the size of an atom? It turns out that's about 33 divisions. And then going in the other direction, if you were to double the size of the average human, how long would it take, or how many doublings would it take to get to the size of, say, a star? And it happens to be about 30. And so in terms of, thinking of things in scale sizes of doublings, we exist in a scale size that is roughly halfway between, the fundamental particles that make up the universe and stars, the fundamental particles that make up galaxies. And so it really does put it into perspective, the importance of understanding our place in the universe and why we're here and where we're going. And with that, I will say thank you for your time, and we would love to answer any questions you may have.
All right. Thank you, Joe, and thank you, Alyssa. I want to start with a question about Hubble versus Webb. And Joe, you did a good job of showing that, they show different things, especially those background galaxies that Webb sees so much better than Hubble. But I wanted to know if there are different image processing techniques or a different mindset you use, because you two process Hubble one day and then Webb the next day and everything. So are there different techniques or thoughts you use, or really just does the same techniques apply to all of the astronomical data you deal with?
That's a good question.
Yeah.
Are you looking at me?
Yeah, I'm looking at you, Lisa.
Okay. Yeah, no, so I would say the overall process is like very similar. Like I feel like the mindset is very similar. I think with Webb, at least for the early release images, since the reference files and the calibration files, it just took a while to get used to dealing with that and those sort of artifacts, that takes a little bit more time to kind of get it set up. While with Hubble's pipeline, it's so refined after all these years that the data is just so clean that you kind of can just jump right into it. So I think that with Webb, it's just the setup takes a little bit longer. And I would say that's like the biggest difference. And then like, as Joe said, like you really want to bring out the faintest things, because like that could be a galaxy that no one's ever seen before. So you concentrate on really, and you do this with all astronomy images, but particularly with Webb, we're really concentrating on sort of gaining the best signal, but suppressing the noise, but really bringing out those faint details that, are the early universe. So that's kind of what we keep in mind, I think.
Joe, do you have anything you want to add to that?
Yeah, I was just going to say, building on what Alyssa said, the process is remarkably similar, processing Webb data versus Hubble. We're using that same approach of applying color chromatically. It's just that with Webb, we're working in infrared, but it's the same process. It's just, applying color according to wavelength. And there are subtle differences between the two. Of course, the diffraction patterns of stars in Hubble versus Webb are very different. And of course, the instrumental artifacts that we have to deal with between the two observatories are different. And so we have to address them differently, but otherwise it is very similar.
Okay, great. All right. So the other question that I can't help but asking, being the astronomer on the visualization team, working so close with you guys, is that I truly appreciate that you guys have astronomy degrees in your background, as well as being these image processors. And Alyssa, you have your art and design degree as well. And you mentioned a lot in your discussion how you go back and forth with the scientists, okay? So could you just, elaborate a little bit more on this combination of art and science? And to me, that's sort of the crucial point that people don't get, that it's not just all science and it's not just all art. It really is that collaboration. So Joe, you want to start us off here on this one?
Sure, yeah. So again, not to beat a dead horse here, but chromatic ordering is so important and it's scientifically driven. The reason why we apply color the way we do is because of the science. And everything that we do when we're processing these images is with respect to the original source data. We're not trying to introduce things that weren't there, and we're not trying to take things away that are there, with the exception of the instrumental artifacts, things that we know are imparted because of the optical system of whatever telescope we're working with. So it requires the knowledge of the objects that you're looking at, to have a good idea of what this should generally look like, right? So as a starting point, when you pull that color image together, knowing kind of generally what the final image should look like really helps. And so having that background in astronomy informs the decisions we make as image processors to get to that point. And I'll let Alyssa pick it up.
Alyssa, you mentioned things about knowing that this is dust and this is the ionizing gas or et cetera in the stars. And so how important is it to have that astronomical knowledge as you're doing the image processing?
It definitely helps just to have that sort of intuition, because you have a little bit of insight there while you're processing the image, and then it's a little bit easier for Hubble imagery in the sense of those symbols that we've developed or connections we've developed, like with galaxies. We know that those really bright blue stars, that represents these young stars, and that's why they're blue. And then of course, if we're looking at sort of the dust, they're kind of like this reddy dusty areas, and the spiral arms are sort of the cooler dust. And those are sort of things that you're looking out for, just little keys that you want to make sure is reinforcing the story. Because if you start showing things that don't reinforce the story, it gets confusing. So you want to build off of what we've already developed, sort of this legend that's sort of been built in astronomy conventions. But again, doing it in a way that's interesting and exciting. So, but yeah, it's definitely, it's a combination.
Yeah. And you're going to develop a close personal relationship with polycyclic aromatic hydrocarbons over the next few years, right?
Oh my God. Joe is right. I could never say that. Right.
We love dust.
All right. So Grant Justice is going to join us here. He's been following the chat on YouTube and picking out questions out of YouTube. So Grant, why don't you turn on your video and give us some questions from the chat?
So why do processors use different tones when processing images, not the graphical colors of the filters? This person says when they use the graphical tones specified in the graph of the telescope filters, they get different than what they see.
Okay, so yeah, I'll jump in, and I think with the question is referring to the actual color of the filter, right? So, yeah. And this would be applicable to Hubble data because Hubble is a visible telescope. With Webb, it's infrared, right? So it's beyond any color that we can see. But certainly for Hubble, in general, if we're doing a wideband color image, we might use red, green, and blue filters, and those would be colored red, green, and blue. It's when we get into doing narrowband or combinations of narrowband with broadband where the choice of colors is important, and being able to have the flexibility to slide those colors around within the visible spectrum, because you may only have, 3 filters that are sort of centered around red. And so if you color them all red, you're going to get a very red image, and it's not going to look very good. So if you take the shortest wavelength and give it blue, and then green and red, you'll get a more aesthetically pleasing, but also a more scientifically informative image.
Yeah. Have you guys done many narrowband filters from Webb where you've had to do the specific color choices, Alyssa?
Not quite. I didn't keep it perfect in relationship to the spectrum, I suppose, and that there's like we like maintain sort of the spacing exactly. It really is what Joe suggested. Even though we're using narrowband, it's really a way to get a color balanced image, which is very difficult with narrowband, again, because we're not capturing the full, sort of covering the full spectrum. And also it's just about separating the colors enough so we can actually differentiate the different structures and processes. And like Joe mentioned, if you have two narrowband filters that are very close together, sort of on the longer wavelength end, and they're both red, then you're losing information rather than gaining information. So you want a little bit more separation. So maybe they're both on the redder end, but you make one orange and one red so you can actually get the information that those filters are giving you.
Right. And I will say, as an astronomer, it's important when you look at these color images to be able to differentiate between the two filters, because that's what you're trying to do to gain the insight in terms of, oh, well, you know, the silicon filter is seeing this, and then the oxygen filter is seeing this, and you'll be able to then guide your analysis of this.
Yeah, this is directly related to the origins of the Hubble palette. You know, any astrophotographers out there will know the Hubble palette. It's because of this.
So that actually leads us perfectly into the next question, which is from Niels. I mean, first off, everyone loves the images, but you already knew that. That's why you're here. What is it that it actually tells you when you are looking at those images? Like, we're bringing it all the way back. I know you've already done a talk on this. I would highly suggest looking up Joe's other talk that he's done with us, by the way. But bringing it back as to like why we're doing this in the first place. What is it that it shows you when you separate it out, when you combine it into this?
So, Grant, are you asking the RGB images, what people get out of the RGB images?
Yes, yes. Okay. The RGB images, along with a little bit of the spectroscopy involved.
Alyssa?
So, yeah, this depends really on the object that we're looking at, right? So, which gets a little bit confusing. We apply chromatic order, so that relationship remains the same, but what it's telling you is different. So, like, for instance, with the deep field, as Joe mentioned, the redder galaxies are further away, or they're more dusty. But in general, the smaller, redder galaxies are further away, and things that are nearest to you, like, are more white, more blue, more yellow. And so you're actually differentiating things. The color is actually showing you distances. But if you're looking at something closer to us, like the Carina Nebula, that's showing you more of sort of the temperature of these gases and their composition, where they're located. So you're differentiating things like if you're looking through the dust, and you see like a really red star, that's like it's a cooler star because it's embedded within this dust region. So these cues are kind of different depending on the image you're looking at. But again, that chromatic ordering is separating like temperature, processes, or distances, or even more if you're looking at sort of spectra and beyond.
Yeah, it's giving you an insight into the astrophysics that drives the appearance of the image that you're looking at. Yeah. So, you know, Grant, behind you, you have 30 Doradus, the Tarantula Nebula, and you've got, you know, on the left side of you, or at least the way I see it, you've got the NIRCam image, right? And on the right side, you've got NIRCam and MIRI, so mid-infrared wavelengths of the same region, right? So that's actually showing you something really interesting. You're seeing the same, like that cluster of young stars that's really bright blue on the left, sorry, which is now blocked by Grant's chair. That cluster of stars almost completely disappears in the mid-infrared. It's gone, right? Those stars, just like we saw with Carina, the stars, they show up in NIRCam and then they're gone in MIRI, in mid-infrared wavelengths. There's astrophysics there. There's a reason for that. And the colors tell us something about that.
Yeah. And let me just say that from an astronomer's point of view, these RGB images are not the ones that they're going to do the science with, okay? Right. But they can help guide the science by pulling out features that astronomer goes, hey, and then he goes back to the black and white images and processes those through his analysis software to pull out the information he's looking for. So the science is always done with the high dynamic range black and white images. But it doesn't mean astronomers are human. You give them a nice color image, they start to see more in it. And the Joe's comment about how stars appear in the near infrared but don't appear in the mid infrared was one of the interesting things that we thought about before we got those first images, right? Because we chatted about it in our group discussions that like, wait a minute, we're just the stars, you know, in Spitzer only appeared in the blue channels, right? And so It adds a whole new dimension to processing these images.
Absolutely. I actually like this next question. Have you seen any JWST images that have been processed by someone else? And if so, what did you think about them? I love this.
Oh, this is a booby trap question.
It is.
I'll keep it simple. No, it definitely yes. And it's very exciting. It's so cool to see the response from people about Webb. The fact that it's showing you that people can access the data, like anyone can access the data. It can be a little bit hard to navigate sort of this archive, but if you go to mass.stsci.edu, you can go grab all the data that's been taken from Hubble and Webb. There might be a proprietary period where you have to wait 6 months, but max a year, but most of the data is already available. And it's nice to see what people think of, because again, like I mentioned before, not everyone's going to see the image the same way. And when we're processing an image, Joe and I are very much guided by the science discovery. So we're kind of following the lead of the scientist, while someone else who is processing the data might see something else that they find interesting that they want to show. And so having that different lens and that perspective is really cool, and it's fun to see. We might be a little jealous that you got to process it, but that's about it.
Yeah, I find it hugely inspiring to see how inspired people are by Webb, and they have a desire to go in and understand more fundamentally how it works and get the data and work with that data and make their own versions of the images. That's great, and I wholly encourage it.
And this is seriously a change from when we were doing Hubble image only a decade or so ago, right? People didn't go into MAST and regularly process them. And now everyone got really excited about Webb, and we got a lot of groundswell of people doing this. So this is really, really good for getting astronomy out there.
Yeah.
And Joe, that leads us to, would you say something about NASA's Astrophoto Challenge?
I was just going
project
to say
you're
that.
involved in. Thank you.
Yes. So if you are interested in working with real data from NASA observatories, we've made it somewhat easier to get to the data through a program called NASA's Astrophoto Challenge. And what that is, if you Google Astrophoto Challenge or NASA's Astrophoto Challenge, you have the opportunity to work with real data from Hubble and Webb and Spitzer and Chandra, and something called the Micro Observatory, which is ground-based observatories. And you can take that data and make your own images from the real data and submit them to be analyzed or viewed by professional astronomers. It's a great program we've been running for years on different objects. The one that's currently running is looking at the Pillars of Creation image that was recently released. Well, the Webb image that was recently released, but there's data from Hubble, Webb, Spitzer, and Chandra, I believe, in that challenge.
Yeah. And that challenge runs through February 28th, if I remember correctly.
That's right. Yeah.
Okay. So get to it, and you can process you can do your own interpretation of some NASA data.
Right. All right. Without having to go through the archive.
All right, Grant, after that plug, let's get back to the questions.
Are the single image processes applied differently when animations/zooms are created? This is probably more for Frank.
Well, no, it's not actually, because when we need a zoom into an image, the visualization, that's more the 3D work. But Alyssa is our master of the zooms to get into these images. You want to talk a little bit about that?
Ooh, I'm learning things.
Yes. So I'm trying to remember the first part of that question, which I think was like creating the animation like between frames. Is that the question? Like I'm not sure if I understood the first part.
The question was, are the single image processes applied differently when animations or zooms are created?
Yes. So the overall process is the same in the sense that we still want to make like the best, most compelling image that we feel that we can make and bringing out the details, but we might adjust it sort of in the end. But usually what happens when we make a zoom image, so to speak, like if we're doing an image for Webb, and is we process the Webb image, and then we get sort of these intermediate images, like the ground-based telescopes. We use Fuji a lot, and then we go into sort of a more intermediate one in between Webb and DSS, for example. And we usually actually adjust those wider context fields, because it's easier to adjust those than to sort of go in and adjust sort of these much smaller field of views where like that sort of stretch is very important to it. And like that was just like, you worked very hard to get that stretch, to bring out that detail. So you don't want to kind of like undo it, so to speak. So generally the process is overall the same, in order to make sort of those seamless transitions between one or the other in terms of like color balance or tonality or contrast. So yeah, I would say like the other plates that we use to zoom in to the final image are the ones that we usually adjust. Hopefully that.
Okay. And Joe, could you elaborate further on that? So like when we create the 3D visualizations and we're flying into an image,
Right.
What sort of image processing is required there?
Yeah, so those visualizations, they're based on the actual image that we built from the data, right? So we take an image, say, last year we did Hickson Compact Group 40, HCG 40 for Hubble's anniversary, and then we did a 3D fly-through of that. And the 3D fly-through is built from the press release image. We actually go in, and the image processing that takes place is to actually extract the different parts of the image. So we'll pull the stars out, and then we'll pull the galaxies out and make them separate layers. So they're coming directly from the image itself, and then they're placed in 3D space. And then the only thing that you have to fill in the background, right? If you pull the galaxy out, we don't know what's behind the galaxy. So we sort of fill that in with sort of the average background level of sky. So then that gives you this depth perception as you're moving in towards it. You see the galaxy moving against the background. That's how we go through that process.
Right. And the process is even more complicated when it comes to nebulae, because you pull off the front layer of the nebulae. What's behind it? You got to fill in that stuff. And so like when we did Cosmic Reef, we had all sorts of fill in and such to work on those.
Yeah, but the good thing about it is that we, working at Space Telescope, we have access to plenty of astronomers who, it's their life's work is to work on these objects. And so we consult with them and make sure that the decisions that we're making, that the artistic decisions we're making as image processors or as visualizers make sense and could be, plausible, scientifically speaking.
Yep. All right. Grant, what else we got?
Is STScI/NASA making attempts to process or present the data in some way that can be seen by visually impaired people? Like, are we doing accessibility for any of these images other than the alt text, which we're already doing? Chat, if you haven't seen the alt text for the web images, go see it. It's amazing.
Right. I mean,
yes.
that's obviously the first answer is about.
Yes.
Now, do either of you want to comment on the alt text?
I think it's great. Our writers have done an excellent job of taking alt text to a new level, right? Really describing everything you see in these images in such exquisite detail.
Because usually the alt text just says image of Carina Nebula.
Right, exactly.
And they've taken it and they've turned it into a visual description of the image. And so the thing I have in my head about what alt text is this isn't it. This is a pure visual description. Now, we have other projects that we work with for the 3D printing of like they did of Stefan's quintet.
Right.
You want to talk about that?
Yes. So we have like sort of almost like a relief map that's built up from the MIRI image of Stefan's quintet. And what that is, it's like a table, like a physical table, where you have the image sort of represented on the table, and then the brightness levels of the image corresponds to depth of bumpiness, right? So you can sort of move your hand across the image and feel where there may be a bright star. There's going to be like a big bump on the table. Additionally to that, there are audio snips that actually correspond to different parts of the image. So you can, move your hand across something, and then you'll interact with a button, and that button tells you something about that specific part of the image. So this is, an attempt to reach out to a broader audience and engage people, blind and low vision people.
Right. And I will just mention that in addition to that, a project that's based at Space Telescope, NASA's Universe of Learning, has an accessible learning resources project that's based out of up in Boston at the Center for Astrophysics, where Joe used to be. And they will also do visual descriptions. They will also do 3D printing things as well as sonification. They'll run a line across an image and have the pixels translated into sound. So there's a variety of those things. Yeah. Actually, somebody asked something about angstroms, which was really just a unit thing. Alyssa, you want to explain what an angstrom is?
It's just another way to describe a wavelength. So like nanometers is like 10 to the 9th, we'll say, or that's like how I remember it in my brain. And then like angstrom is it's -10. So it's just like a helpful way to use it for science. I honestly, this is like back from my astronomy days, so I'm probably not to talk about it. But like, for instance, like to describe wavelengths for Webb, we use microns because it just makes the most sense, because that's just the easiest way to show that number. But it really just depends on what wavelength or what sort of part of the electromagnetic spectrum you're working on and what makes sense to you. So yeah, it's just a different unit. Make sure you pay attention to those.
Yeah. It's an astronomy specific unit. Yeah, it's an astronomy specific unit. Right. And it's more for X-ray astronomy, right, Joe?
Angstroms?
It's you get down to a few angstroms. You're X-rays, aren't you?
Yeah, true. Yeah. I mean, I usually think of it in electron volts, but yeah.
Yet another unit. Specific to that astronomers use all the time. Yeah. So we do have some interesting jargon in our field. How about that?
Yeah.
All righty. Thank you so much, Joe. Thank you so much, Alyssa. And thank you, of course, Grant. This has been a lot of fun. I'm sure we'll get, you guys will get a lot more requests to do these talks, because everyone's just so interested in the Webb images, and seeing how they are made just, turns on a light for so many people.
Imagine you had a universe which was a Googolplex meters across, okay? So big universe. Then that's very big. And if you actually traveled far enough in that universe, you would start to see repetitions. You would start to see exact copies of yourself.
Today we've got a Googol.
A Googol?
A Googol.
As in the website?
Kind of, not spelt the same. It's spelt Googol. 10 to the power of 100. So imagine that that's a 1 with 100 zeros after it.
And it was it came about because it was a guy called Kasner, who was a mathematician. He was also very famous in cosmology.
Now, it wasn't him that came up with the name. He just thought of a really big number. He thought, what's a big number? 1 with 100 zeros.
And he wanted to sort of explain infinity, and he wanted to come up with a very big number that wasn't really big at all compared to infinity.
And he actually asked his nephew, his 9-year-old nephew, what's a good name to call this number? His
nephew came up with the word Google. But it's quite a big number. I don't think it's that big a number, but it's quite a big number. I mean, to put it into perspective, you might ask yourself, well, okay, how many grains of sand could you fit inside this room? Okay, you think that's a lot, right? That's going to be a lot of grains of sand. It's only about 50 billion. Not that much. So you might ask, well, let's ask something more dramatic. Well, how many particles are there in the universe? Okay, now that's 10 to the 80. 10 with a 1 with 80 zeros after it. That's how many particles there are in the universe. So a Googol is bigger than that. And you could ask yourself, okay, well, how many grains of sand could I fit in the universe? Say the universe was full of just grains of sand. How many grains of sand can I fit in the universe? And that would be about 10 to the 90, so 1 with 90 zeros after it. It's quite a big number, but it's not that big. There's certainly stuff that's a lot bigger than that.
You're saying it's not that big a number, and yet all these things that we think of as big, like the size of the universe and atoms in the universe and particles, aren't even touching it. So it must be big.
Well, yeah, okay, but I can think of something that is bigger than it. That's physical, that you can think of physically. So if you take the smallest volume in the universe, something like, which is a Planck volume, so it's basically a little cube its radius is a Planck length, which is 10 to the minus 35 meters, okay? And you see how many of them you can fit in the observable universe, and you get about 10 to the 183. So that's a 1 with 183 zeros after it. So that is bigger than a Googol, okay? So Googles aren't that impressive, so, because we can think of things that are bigger.
He then thought, well, what's a bigger number than a Googol? And for that, he took 10 and raised it to this power, the power of a Googol, 10 to the 100. So this is taking 10 and timesing it by 10 and 10 and 10 and 10 and 10 and timesing it Googol amount of times. And this number is called a Googolplex.
We start writing down a Googolplex, okay? And let's suppose, well, we're writing on a piece of paper here, but let's suppose we actually try to write it down on particles. So for each particle, we're going to write down a 0. So first particle, we write down a 0. Second particle, we write down a 0. And we carry on doing that on every particle in the universe, and we still would not be able to write down a Googolplex. It's too big a number. And there's something else remarkable about a Googolplex. So I find this astonishing. Imagine you had a universe. This sort of emphasizes how big a Googolplex is. Imagine you had a universe which was a Googolplex meters across. Okay, so big universe. And in some models of internal inflation, things like that, you do get universes which could be as big as this. So we have a universe which is a Googolplex meters across. Then that's very big. And if you actually traveled far enough in that universe, you would start to see repetitions. You would start to see exact copies of yourself. Now you might think, what the hell am I talking about here, Brady? But you know, let's take you, Brady. Let's ask how many quantum states can describe the volume that you occupy. Okay, right? The number of quantum states that can occupy that volume, the total number, is, and you can work this out. It's something to do with entropy and black holes and stuff like that. But you can work it out, and it is 10 to the 10 to the 70. That's a number of different quantum states, different ways that you could actually put together that volume of space. So let's say, so that number is less than a Googolplex. Why?
So the space I'm in could be me, it could be you, it could be a dog, it could be a vacuum, it could be anything.
It could be all those particles arranged in any number of different ways. Particles might not even be there. But all those possible states, given that volume that you occupy, the number that you could, the number of possible states you could have is 10 to the 10 to the 70. Big number. Not as big as a Googolplex, but 10 to the Googol is equal to 10 to the 10 to the 100. Okay, so this number is clearly less than this number. Okay, so you occupy roughly about a meter cubed of space. There's that many different possible states that you could be in. Okay, so if you go this many meters away from yourself, you know, you would start to expect to see repetitions. So that means that if you're in a universe which is so big, as big as a Googolplex meters across, then eventually you would start to see repetitions of those volumes of 1 meter cubed.
So just by chance, I will run into another arrangement of atoms that matches me.
Exactly. Matches you exactly. And then, you know, you go even bigger and you would start to see sort of, you know, entire observable universes repeated. So this is truly remarkable. I think the fact that you would go there and see your doppelganger if you went far enough away in a Googolplexian universe, I think is just sort of emphasises how big that number really is. But the size of the universe is 10 to the 26 meters, sort of all cubed. That's the size of the universe. So this number is, you know, tiny compared to that.
So there's probably not another me in this universe.
Probably not. But if we live in a universe which is a Googolplex across, then there probably is.
We love pi, of course, everyone loves pi, but one of my favourite pi facts is, and it's, I think it's fun, you only need 39 digits of pi to be able to measure the circumference of the observable universe within the width of 1 hydrogen atom, and that's all you need. So we write out the 39 digits.
Yep.
Let's put it here. So the 39 digits of pi. It's 3 point. Now 3 counts as one of the digits, so it's now 38 decimal places. Let's do the 38 decimal places. 1, 4, 1, 6, 5, 9, 7, 9, 3, 2, 7, 4, 2, 0.
He didn't memorise that, everyone. There you go. Show him what you did, just in case.
Wolfram Alpha app.
Yeah.
Never leave home without it.
Yeah,
right.
right. So he's not a pi. You're not a pi memoriser, James.
No, I'm not. No, and that's another thing altogether. People who memorise this this pi figure to a massive amount of digits, but people who calculate it using computers have calculated it to currently 10 trillion digits of pi.
Go on then, let's do them.
Okay.
All right. No.
So that would be all you need, and that's overkill as it is, because that's all you need to measure the circumference of the observable universe. So the observable universe is the distance that light has travelled since the Big Bang, and if we say it's travelled in a big sphere, in a big bubble, then if we measure the distance around it, we'd have the circumference of the universe, and we would need pi to work out that circumference, and we could be as accurate as a hydrogen atom if we use just 39 digits of pi. We don't need to use the whole thing, of course, which goes on forever. So in fact, in practical day-to-day use, in engineering, in real life, you would only need a handful of digits of pi to have an accuracy that would be suitable for anything that you need to do. So Wolfram Alpha told me that the diameter of the universe was 8.8 times 10 to the 26 meters. So that's the diameter of the observable universe. If we want to work out the circumference then, we times it by pi. So the circumference would be pi times the diameter. What's the difference when I take away my truncated pi? What I mean is, what if I took away my pi with 39 digits, I've called it pi 39, and did the same thing, times by d. So that's the real circumference of the universe. Take away my approximation. What's the difference? If I do that, what I got was actually around about 2.5 times 10 to the minus 12 meters. So that's how accurate, that's the difference between my approximation and the real value. That's how accurate it is. And a hydrogen atom, Wolfram Alpha told me, had a diameter of about 2.5 times 10 to the minus 11 meters. So in fact, this is more accurate. This is more accurate than a hydrogen atom. So why do we calculate pi to 10 trillion digits? These days, it's a way to test our computers, our supercomputers and our algorithms. It's a way to test them to see how good they are. That's why computer scientists are interested in this sort of thing. Mathematicians have tried to do this for thousands of years out of curiosity. So it started with Archimedes. He tried to get an accurate idea of pi around about 250 BC. He didn't have decimals in those days, he had to use fractions, but he had tried to work it out. Then in the 17th century, there was a Dutch mathematician called, now I'll probably anglicise his Dutch name, I apologise. He was called Ludolf van Keulen, and his life's work was working out the digits of pi. And by the end of his life, he had worked out 35 digits of pi, and they're on his tombstone, which is kind of cool, isn't it? It's kind of neat. We skip on to the 19th century. There was a guy who had about 707 digits of pi. This was the authoritative example of pi for 100 years, until 1945, and they found a mistake. I know, shock, horror, they found a mistake, and the last 180 digits were wrong. Because somewhere along in his calculations, somewhere around the 500th decimal point, he had made a mistake. And from that point on, everything else was wrong. What a disaster. Fortunately, we were able to use computers by this point. So in 1949, ENIAC, the American computer, was able to calculate pi to 2,000 digits. So suddenly, it just exploded after that. Once we've got computers, it just exploded. We had more and more digits of pi, and now we've got 10 trillion digits of pi.
Okay, who knows numbers of pi? I know Piper. Yeah. Yeah, that's a good start. Okay, we'll now close with the SpaceX launch from a couple of days ago from their South Texas launch site and the chopsticks recovery. Just to put it into context, the booster, the super heavy booster that is on the bottom stage, the first stage, is 71 metres high, 9 metres in diameter. So the diameter of it is pretty much the width of this room. So it's a fair lump of steel. And the two masses there, 3,600 and 275, is its full of fuel and empty mass. So in other words, when that came back and was captured, it caught 275 tonnes, which is a fair whack dropping out of the sky at supersonic speed. The Starship stage that sits on top of it is 50 metres high and also 9 metres diameter, obviously, and it can hold over 1,000 tonnes, and empty it's 100 tonnes. So this is the heavy lifting one that's going to go to the moon and go to Mars and take lots and lots of things into orbit. Now, interestingly, the SpaceX target for bringing these things and capturing it on the arms is to turn it around in 1 hour. So in other words, it comes down, lands there, they immediately fill it full of fuel again and launch it up again within the hour, right? That's what they're aiming for. So this is the first step to capture it, and now we'll see how many times these things go around, and there's metal fatigue and those sort of things happening, I would expect. Why? It didn't fail this time. It took them five goes, of course. This is the fifth one. Oh yes, yeah, but all 30 of them were going there. You could see the pattern of which rockets were going, sort of shown down on the left-hand side of that screen. But yeah, pretty impressive. But remains to be seen how reusable it is before they can't fly it again the next time. Yeah, I would have thought that as well. Yes. All right, with that, I'll close the meeting, and hopefully we'll see you for the last meeting for the year, which is the November meeting.